All right. All right, you guys ready? So, for some of you, this is going to be backward, or you guys over here, it's coming at you. You guys over here, it's going away. But I'm going to draw the representation up here in a second. But as I suggested, I have this this ball bearing. Now, I like this because you can hear it. True? Okay? You can hear it. So let's listen to it. Does it sound like it's slowing down? No, it doesn't, right? And so when it's on this part, I'm good now, thank you. When I'm on this part, did you notice it speeding up?
Yeah.
And when it's on this part, did you notice it going constant?
Yeah.
Is that okay?
Yeah.
So I could do this here, I got it. Speeding up, going constant. You good with that? All right. So if we were to draw this, we're going to try to represent some things that are going on here.
What
Okay?
side of our notebook do you want to start?
So just open to a new page. Just open to a new page.
My specialty. Who do you want?
Okay? And I can.
You know what?
No, it's not.
All right. What does the A stand for? A is the acceleration. V,
Velocity.
velocity. X.
Position.
So we just use X as a generic position. Is that cool? You guys okay with that? All right. And where are we starting our ball? Up here. Now, we're only going to talk about left and right here. So the left side of the ramp is position 0. Now, I know it goes down and then straight right. Don't worry about the down part. It's moving away from the position. Okay? In the first part, we know it's speeding up and then going constant. True?
True.
Okay? So we have a sense of that. So I want you to think about the position, velocity, and acceleration graphs. Check with your neighbors and go ahead and try to sketch a graph. What do you think? Okay? What do you think the position, velocity, and acceleration graphs are going to look like? Okay? Draw that right now. You and I are on a collision course. Like you're on a collision course, or when we did not help you. You with me on that?
Yeah, like that.
And you can make that decision. I don't have to explain, but
I just live
What is that reciprocity?
Oh, yeah, you're right.
So it goes exponentially ahead.
So like just like that, like a regular.
Not the whole thing, right?
Yeah, the velocity was no, because it accelerates and then it
Yeah, that's
down. It'll have a slope and then it'll be straight.
yeah, that's what I was like.
No, I didn't. Okay, yeah, that's good. Acceleration. It's an acceleration.
Yeah, I don't know.
It would start as a parabola and end up as a slope.
So this would be constant speed. Then you don't have to speed up and then go.
Acceleration might be
So you think I know?
accelerating.
Is that for the position graph, Mr. Nettle?
What's that?
Is that for the position graph?
Oh, no, that's just
You have to speed up and then go constant.
velocity.
What can't you see?
Put on your glasses. I lost my glasses.
So it starts slow.
Yeah, and I can't put my mom to
You gotta make sure
Yeah.
So it's like something like that.
So I like that.
It'd be like on the velocity, like there's no line in between them, but it would just go from.
What's going on there?
Kind of messed up.
No,
It's a little imperfect.
All right, you guys ready? So, I love where you're at, okay? I love where you're at. So, let's talk about the position graph, okay? Let's talk about the position graph. Where's the object start?
0.
At 0. Now, if we just look at this first rampy section, you guys did a whole lab on the ramp section, true? Right? Where you rolled the ball down and you marked the position. What shape does it have to have when it's on the rampy section?
Parabola.
It's got to be a parabola, right? So starts, right, like this, okay? How's that look? that cool?
Yay.
So we got a parabola to there. Is that cool? And then it gets on the flat section. What do we know about the speed then? It's going to be constant. Now, many of you drew this, where you drew to this, and then you drew like that, which is the right conceptual framework, just the wrong execution. So in this, you have it getting steeper, and then less steep. That would be if it sped up, and then when it got on the flat part, it slowed down and went constant.
It would just be.
So we need your flat section to be tangent to the last part. So it is, you have a parabola to here and then linear from there. So that has speeding up and then going constant. Is that cool? You good with that? Now, what I like about this activity is that it's basically taking all the work we did with constant velocity before, where this was linear, and now we're kind of melding it together with the acceleration, with the constant acceleration. All right, what about the velocity? What about the velocity? Yes?
It would be increasing linearly until it flatlined and stayed the same.
I love that. Did you guys hear what Ray said? He said, look, we already did this lab, we already did both these labs, right? Where when it's on the ramp, it increases linearly, and then when it's on the flat part, it's horizontal, right? Now, I like to stack these graphs because you can say like, this is when it changed, this is when it changed, this is when it changed, right? So he said, starts with 0 velocity because you let it go, increases linearly, and then goes constant. How's that? Is that consistent with your ideas? It is, because I already saw them. I walked around and I looked. What about the acceleration?
Straight line above 0 and then a 0 line.
Where's your acceleration? Don't wait for me, man. Don't wait for me. Don't wait for me.
Oh, you're mad, I get that.
Listen, don't wait for me. It's not a secret.
I No, I don't know.
So, what is our definition for acceleration? Okay, it's the slope of the velocity graph. Are there two sections here? Okay, go ahead. Go ahead.
It would start at like a point like, it would start at like, I guess 2 would be the intercept that it starts at. And then it would go for like however long seconds, and then it would go down to 0 and flatline at 0.
What do you guys think of that? Is that cool?
Yeah.
So it accelerates when it's on the ramp, but when it's on the flat track part, there's no acceleration because there's no change in velocity.
Wait, why is it a straight line?
What's that?
I don't understand, like, why is it a straight line and then it's like,
So if I look at my velocity graph, remember the slope of this is this value. So if I look at this first section here, the slope of this green section
oh,
is constant and positive, so the acceleration value is constant and positive. But for the second section of green, it's horizontal, so the slope is 0, so the acceleration value is 0. And conceptually, it's not speeding up, so the acceleration should be 0. Is that cool?
So I can't see because I have like no sight right now. Is the third graph, is there a line under, like on the line? Like,
Yes,
Okay.
it's right there.
It's a 0 line at 0.
All right, yeah.
But like, once the ball hits like the flat part, isn't it technically slowing down? Like even if because it's got.
Well, maybe, but, I mean, I actually angled this a little bit, so it would kind of, nah,
Yeah.
Friction.
sneaky. Friction actually does a funny thing. Friction doesn't really make things make rolling things slow down. It just makes them roll.
Air resistance?
Maybe, but we're talking about in here, in this section.
Gravity.
Okay?
Gravity's helping.
What's a gravity?
Gravity.
What is a gravity?
It's like
Newton's cradle, that's basically what we're saying. All right. Now, the last part of this is we need to draw the motion map, yeah? Okay? So to draw the motion map, first let me move this ball up a little bit. Okay? What happens to the ball as it goes down the ramp? What happens to the spacing between the balls?
It's larger.
It's getting larger. Why? What's happening?
It's accelerating.
Okay? It gets faster, true? But then what happens to the spacing when it gets on the flat part?
Equals.
The spacing is going to stay the same. Why?
It's the same.
Sound okay? All right, so draw those. Take a moment, put in some velocity and acceleration arrows where appropriate. And I will come around and see how you did. So make sure the spacing between these is bigger than this spacing here, because it still speeds up. Does that make sense? Yeah, you have it. So this spacing here, the spacing on the flat part should be bigger than that one because it still speeds up. Okay? Okay. Listen, you're not glued to the chair. You can move.
Okay,
You go anywhere you want.
Wait, the arrow under is the acceleration.
And then what is the one on top? Is that velocity?
Draw the motion map. Come on. Draw, draw, draw.
I would be honest, this for 2.5 hours. Maybe longer depending
If it's accelerating,
in this traffic.
if it's accelerating, you're going to need some acceleration arrows, yeah?
Look at my pen. Yeah, my palette. What are you doing?
Velocity is like.
All right. If I put the green arrows on, the velocity arrows, couple things. Do I put a velocity arrow on the very first dot?
No.
No.
You sure?
No.
I mean, what's the velocity at time 0?
0.
It's 0. So I'm not going to put one there. What about this first one though? Sure. Second one? Longer. And then what about this?
Those are all
Wait.
equal.
These aren't,
Yeah, there's no acceleration.
oh, these are velocity.
Those are the velocity. So no velocity, some, more, lots, lots, lots.
So the last one should be all the same?
All the last three, on my diagram, the last three are the same. And they're longer than anything else. What about acceleration arrows?
There should be one on the first one. Are they still the same?
Yeah.
How do you know how many arrows to put?
Oh, so we don't know. So what I did is I just said, look, I'm going to represent some. So I know that when it's on this part, they should be getting farther apart. When they're on this part, they should be going the same speed. So they should have the same distance. Yeah,
Should the first dot have an acceleration line?
it should. Do you know how I know?
Because the value is like not 0.
Because at time 0 is the accelerating. Yes, it is. And it's on the ramp, you know.
Beyond arrow or is it just
Do I put acceleration arrows on these?
No.
No, because what happened to the acceleration value? It dropped to 0. So the idea of this whole thing is to represent it in a couple different ways so that your brain tries to make more sense of it. So when I go to look at the relationships between these graphs, for example, I know that by looking at the slope of the position graph, it's going to inform my understanding of the velocity. You see how this starts with 0 slope and gets steeper? That means my object is getting faster. And then here, the slope is constant and positive, so my velocity is constant and positive. I'm going to do the same thing here when I go to analyze. When I go to analyze the velocity graph to find the acceleration, I know it's the slope. So the slope of the velocity graph gives me information about the acceleration. This part's constant and positive. This acceleration is constant and positive. This slope is 0, so this acceleration value is 0. Now, it's super, super easy when I do it, right? But we're going to have to practice. Okay, we're going to have to practice. Are we all good with this one?
Yes.
Ready to try the next one?
Sure.
Sure, they say.
I don't know where I wrote the next one.
Okay, I'm going to take my steel ball bearing, and I'm going to push it up this ramp here. Maybe. Maybe. Okay. Now, we're going to start looking at this after I let it go. We're going to start looking at this after I let it go. What do you think is going to happen to the speed? What's going to happen to the speed after I let it go? I'm going to let it go down and give it a push for right here. Well, it's on this part. I let it go, it's moving fast. What's going to happen to its speed on the way up? Is it going to slow down? And then what happens when it gets on there? Okay. Yeah?
So are we considering that the far left side of that is 0?
Yeah, that's the whole thing. It's always the far left side is 0. Okay, you guys ready? Set? Not enough speed. Let's try again.
Mr. Pat, how is it staying there? Is it stuck on the sticky thing on the desk?
Okay, got a little bit of stick there. Okay, ready? Try again. Man, that was aggressive by me. A little too aggressive. Let's try again. Ready? How was that? Was that good?
Oh, yeah.
You want to try one more time? You guys happy with that?
Yeah.
So what did you notice? After I let it go, what happened to its speed?
Slow down.
Slowed down until it got on the flat part, and then did what?
And then it sped up. It looked like it sped up. From here, it looked like it sped up. Well, there
I'm
is.
sitting next to
It
it.
looks like that's, it's pretty
Here,
maybe this is Connor's spot.
He said.
No, so what happens is, this track is aluminum and it bends a little bit when it's this far apart. So it actually might have a little bit of dip in it.
Yeah.
But let's, for our purposes, can we say it went constant? It didn't significantly speed up or slow down on this section.
It
True?
went really fast on the first part because you pushed it really hard, and then once it stopped.
That's true, thank you, Richard.
But did it slow down here?
I was gonna say around.
It didn't slow down?
Okay, well, the first time you did it, you kind of like chopped it.
Oh, I did. The first time was way too aggressive.
So like that.
Way too aggressive.
That was faster.
Just by having hustle.
Because Ronald Reagan was just handed actually an entire president.
God believe me, we pay the 1%. It's gonna fight for doing it. The 1%.
Yeah, dude, that was one, bro.
No more graphing? Lots of graphing. We are training your brain. We are training your brain.
We're calling everything. Actually, because you could almost.
Okay, so. Well, it's gonna be different because acceleration is decreasing and then.
So what? So they didn't trade it?
Well, it
It'd be
accelerates.
like, I think it'd be something like,
You gotta measure it on
goes
both
up and
sides.
then.
It's like a parabola.
Oh, no, you know what it is? It's like this, it's like
No, but
that.
position is zero.
No, yeah, it's just saying that, yeah, it wouldn't. Not as much in that.
So, couple things.
Like this.
I think that's.
It starts at zero position, but it starts with a large positive velocity. Okay? It starts at zero position, but starts with a large positive velocity. I know it's positive because it slowed down. Ooh, nice. Nice.
Because look, the time in position is gonna go really fast and then the smaller.
Oh, so like the slope almost on the graph, it's softer and then it just goes constant.
Yeah, because it's deaccelerating, so it's gonna start really fast. And then.
Yeah, so it starts with zero position and the position is increasing.
This also means that on the motion graph, it's gonna start with
Because I guess zero. Yeah. Oh my God, wait, does it go to the end? There's a little L and
So you're telling me that it's.
That's like negative.
Well, the square root of the flat is not.
Yeah, that means
The velocity starts.
Starting at a certain
It's like what I had almost.
Okay, it is the inverse.